This second film on optical systems is about optical sources and optical detectors. And we have here an atom, and with the electrons surrounding the core of the atom at given bands. And the electrons really prefer to stay at a band as close to the core as possible. If an electron is excited up here, it would really like to jump back to the lower band where it belongs. Well, you can excite an electron to a higher band if you apply an electrical power. So electrical power is used to excite the electron to a higher level, and then spontaneously, some seconds, milliseconds, microseconds later, it will fall back to its original state. And once it has fallen back, or when it falls back to its original state, it has to get rid of the extra energy somehow. And that is emitted in form of a photon. So one photon is generated due to the fall in energy from a higher level to a lower level. And the energy here is a function of Planck's constant and the frequency that it emits. So the higher the energy, the larger distance between two bands, the higher the energy, higher frequency, shorter wavelength. So in order to make diodes, LEDs, that emit at different colors, we need to create substances that have different gaps between these bands here. So you see, for example, if you have a red LED, it's made of gallium arsenide phosphorus, while you can make other colors like green by making an ally of aluminium, gallium, and phosphorus, for example. And you see the supply voltage here is different, and also the energy is different. The longer wavelengths are here, shorter wavelengths are here, and or also more electrical power required to drive them. White light is a mix of all these colors here, so therefore it requires a lot of power. The good things about the LED is, the benefits of a LED is the long lifetime. There is no mechanical parts in here. There is nothing that glows. You simply get the light from the atomic structure. So they really have a long lifetime. They are also energy effective, which means that they don't produce heat to much extent. They produce light, simply. They withstand harsh environments. They tolerate vibrations and high temperatures, low temperatures. They are really fast. You can turn them on and off really fast. If you have a traditional light bulb with a glowing wire, that wire requires some time to shut down and requires some time to turn on. And they are driven by a rather low voltage compared to traditional lights. Then you have something called a laser. A laser is an abbreviation for light amplified by stimulated emission of radiation. And a laser is a sort of a LED. But the thing is that when you have one atom which produces a photon, that triggers another atom which keeps the old one that you had from before, but generates a new photon, and the photon here is a copy of the old one. And a copy means that it has the same wavelength, and it's also coherent, which means that it has the same phase as and direction as the last one. So therefore the light becomes very intense, because all the copies here that are made have the same wavelength, and they all have the same phase. So that's why it's so effective, for example, burning into materials. That's the coherent properties. But for many applications, we are really interested in this. A very narrow wavelength spectrum compared to a normal LED where you have a wider wavelength spectrum. The laser is I guess you have seen the red beam from a laser, that the red seems very intense compared to a normal LED, and that is due to the avalanche effect of one photon making a copy of itself in an atom. On the optical detectors, I'm not going to go into the technology, how they work, but you basically have three different. You have something called a photoresistor, something called a photodiode, and something called a phototransistor. So this table here is a comparison of photoresistor compared to the diode, and then you take the diode and transistor in the last table. This is more responsive to light, so this one is more sensitive. It's more directional, which can be positive and can be negative. If you don't know where your light is coming from, you should go for the photoresistor. But if you want to protect it from false lights from other directions, you should use a diode. Temperature dependent, resistance varies with temperature. This is has a less sensitivity to temperature. Costs less, and the effective resistance varied with applied voltage, but this one doesn't. So this is you really need to be careful with your choice of voltage source to drive this one. When it comes to the photoresistor compared to the photodiode, you see that the response here is much faster than this one, but this one is more sensitive. So it depends where what your application is. While when they say that this one is slow, it's not very slow actually. It's fast enough to work as a receiver in compact disc players, for example. So it's fast enough for 44 kilohertz. While this one can be used both to generate power and to detect the amount of light.